right. Well, welcome everybody for again today. Um, we got an interesting session today. I hope for you. We're going to work on Frontera, and we're going to do a little exercise here on GeoLab. I'll get to lecture material first, but as I promised, I always start each day with a question. And Tam, in the chat. If you bring up the chat, I'll go through this set of questions. They're listed here. So the first one is, what type of MsPASS error did bundle data to the cemetery? Or what killed, in other words, what kind of error killed something? The way you establish that, it's actually a good way to bring up a different topic, a parallel topic I kind of wanted to do anyway. So let me see if I can find my notebook right here. That's not it. It's right underneath here. There we go. One of the things that I always do when I am working on anything like this, I always create a secondary notebook when I'm working interactively like this. Today we're not going to work on one of these things. We're not interactively, but when you're working on Jupyter, I always produce one of these things like this. The first thing it has in it is just this box, which is creating a client to link to the database that I'm working on. It's a good way as a side to know what things are going on. So you look right down here. I can't remember. One of you was in our help sessions yesterday, pointed out that there was a mistake in one of the questions. I think it was question 2, about how many mini seed documents there were that matched station this. So I said, oh, I don't know. Let's get the answer, right? So that's what I did right here. I ran this like this. I launched the database, and I found out that I had screwed up. So for those of you who went through the quiz early on, or a couple of you got the wrong, you probably found the answer that I had, which was actually the wrong answer. It's 60 with that query. It was my mistake for clicking on something wrong. But now, to get back to your original question, what you do, you have to query the cemetery. So one way to do that is, the first thing is, I can never remember what is in those things, so I'll just do this quick query. Doc equals db.cemetery. Find, why are you doing that? Find one. I don't think I imported this in from, I'm gonna make this, it's pretty ugly to look at this otherwise. This is I just know this one because I use it all the time. So this is what one of the records from the cemetery looked like. So to answer your question, what you do is you would search for this. I'm not going to try to construct that on the fly here, but yeah, it's a little weird because you have to hunt into the log file. There's actually should be in here somewhere else too. But the answer is, you have to construct a little bit more elaborate query to find it. And then you got to find the error message that showed it. So I would have to search for algorithm as bundle seed data, and then you pull out this thing, which is the error message. This one showed that this one was killed because window data, the window didn't overlap. And that happens commonly that's a very common data problem. Even a gap or something that segments the data in the window you want, it's not going to work for it. And the way we had it set up, it'll just kill that thing. There's other options for window data to fill and that kind of thing, but that's a detail. So hopefully did that answer that question for who asked for that? Now what's my next question? Is that okay? Did you get where was the other one here? Do I have to stop share? I guess I do have to stop share maybe to get this chat up. I don't know who left that. Did I answer the question? Did he? Is that okay? good enough anyway? I mean, that's the answer. That's the general way that anything that kills something leaves a record in cemetery with that error log message. And then you have to paw through the error messages to figure it out. Something, frankly, that I need to work on is utilities to make it a little easier to browse those things, because you could get a lot of errors sometimes, and it can be hard to paw through them to find all the problems. But that's another story. Any details on the final project? That's easy. There is, I think there should be a document on Moodle at the very end. There's a thing about the final project. We'll talk about that on Friday at a little bit more time, but it's there's some details in there about the way we're going to do it and so on. So I'd say just look at Moodle. It's like toward the end. So the last question is this is a little longer. It says, my question is quite, you're reading it, okay? From what I understand, I could rewrite Python codes or use MsPASS to call MsPASS instead. So anyway, you just repeated what I would have said, which is that it really is mainly two things that are distinguishing about MsPASS compared to MsPASS. One is the fact that it has this embedded database that works really well with seismic data. This MongoDB, the way it works, and it's coupled to it, is a big difference. I know there was an attempt, I don't know where it ever landed. Several years ago, the MsPASS team was working on a relational database method of sort of a database to go along with MsPASS. I don't know if I haven't seen anything actually. I think it must have died as far as I can tell, or at least I never saw any more development. Maybe somebody could educate me, but so that's one thing, is when you get lots of stuff, especially when you get million seismogram scale records, or even anything over like a few 100,000, you just cannot manage it without a database effectively. The second one is the parallelism. And that's the really big departure from what MsPASS is capable. There isn't really anything directly in MsPASS that can do that. Now, you could actually do, in the things we're going to talk about today, if you had a really stable, I can tell you right now that if you had a really stable set of data that you knew was going to work on every one of those functions, and you wrote your own error handlers, you actually could parallelize any MsPASS workflow. It's a little tricky. It has to be driven a different way, but it is feasible to do that. Actually, I'm going to add a third thing, and it comes up today and tomorrow and Friday. And that is one of the problems about the design of MsPASS for large data sets is a dependence upon files as input and outputs. And that is, I don't know how much time I'll have to harp about it on HPC systems and on the cloud, but more on HP systems, it is really evil to make millions of small files. You will be a bad citizen if you try to build 1 million files on an HPC file system. It just, not only, you might just crash it's possible to crash the system by trying to manipulate something like that. So anyway, I don't think we have time to get into that today, but that's my answer to that long question. So is there anything else anybody else wants to talk about right now before we get going today? Any other questions that came up? Going once?
Unmute yourselves.
Going once? Twice? All right, well, let's go then. I have, you found the right page. How about that? Okay. So I will go on that one. So we just did the first thing. So here's what we're going to do today, just so you kind of know where we're going to go. I'm going to give a 10-minute lecture here on sort of some fundamental things that are kind of to make sure there aren't some conceptual barriers for how an HPC system works. I don't know how many of you have actually worked on a large cluster, what would be called an HPC cluster. So maybe a lot of this material may be introductory to you, but I suspect not everyone. So if not, it's think of everyone's an expert and everyone's an idiot. So some of you are probably complete experts in this already, and some of you don't know anything about it. So I have to cover this because I know there are some conceptual barriers here we're going to run into if I don't. Then we're going to set up and run a great big processing job that runs for about 45 minutes on Frontera on just one node, but with multi-processing with like 40 workers is the term we'll use. And then while that's running, we're going to jump over to GeoLab, back to GeoLab, and run a little exercise. It's kind of doing a similar thing, but it'll allow me to talk about parallelization and how the parallelization model that's used in MsPASS called MapReduce works and what's going on while you're running this job on Frontera. And then at the end, we'll come back and see, look at hopefully our jobs will complete. Doesn't really matter if they did. It's just the idea is the exercise about how we have to do this. So anyway, that's the plan. So one of the things you might do right now is that make sure you have GeoLab running because we're going to come back to it. In fact, we're going to need it in a few minutes. And I'm going to show you what you kind of need to have. You're going to want to have this thing, these directions open. It's in this folder called TAC files. You want to open this thing called HPC preparation. We're going to go through those instructions in a few minutes. And later you're going to use session 2. And we're actually going to open some files in here too, but I'll get to that in a minute, okay? So anyway, so the point is be in GeoLab, and don't forget to push the right buttons when you start, and we'll come back to this in a few minutes. So here's my short little introduction to some things here. First of all, I want to remind you of the introductory lecture I had online before you started class. Some terms, cores, blades, I assume you know that by now. What I really want to talk about that introduce this today is something that might be foreign to some of you called batch processing. I'll talk about that in a second. And then the idea of the so-called job schedulers that are used on HPC systems, and the idea of services of the way MsPASS works on an HPC system, because you need to understand that, because then what we're going to do is a configuration to run our individual jobs on Frontera. So I'm going to try to give you the background on why the heck you're going to do that and what that's all about, okay? So first, a reminder, there's a picture, not a very good one, but a picture of Frontera, the supercomputer you're going to run on in a little bit. And a reminder that these things, a modern supercomputer or a cluster is just made up of a bunch of stack of blades, which are individual computers. So each one of these little pieces in this rack is one computer. So there's like 30, 20 of them there. I don't remember, a little less than 10, 15. I don't know what it is. I can't count that fast. They're in that rack, and there's a whole bunch of racks, and they're all linked together. And that's what a supercomputer HPC system is. And in fact, on Friday, you're working on a cloud system, which is that too. Okay, that's the hardware. So there's some words for the introductory lecture I want to remind you of, that there's some terms. So if I use those terms, remember what they are. And a key difference between what makes this weird in a modern cluster, or the way modern systems work, is you have what's on a single blade has shared memory, and you can access that memory really fast. But if you have multiple blades assigned to the same job and you want them to share work, you got to move data back and forth between them on a different method. You don't just have direct access to that memory. It's called distributed memory because it's spread out among all those nodes. And that's a big difference in terms of how you actually do everything. But the model we're using works really well in that context, and you'll see. Hopefully, you'll be able to see why here shortly. Um, what we're gonna talk about mostly is this last item, the so-called foreman worker model, which is what's used in MsPASS, which is the basis of what's called MapReduce. But step back now. All right, now I thought this an interesting thing to think about, and I may or may not be helpful. But an old guy like me, I couldn't help but just introduce you to this topic. Somebody who's started computing long. When I first did my first computing exercise in the 70s, this is what we did. You prepared a card deck, you submitted it to an operator who ran that card deck through a card reader like this one, and you got a printout back. That's batch. That defines batch processing in the 1970s. The truth is, HPC systems are essentially doing exactly the same thing, except what you run is a lot more sophisticated, and the way you drive it is more sophisticated. In the earliest days of computing, the earliest version of batch processing was on IBM mainframes, and the earliest thing they used for it was a sequence of lines that you typed in, like this is a sequence of lines on a card, and every card would have an instruction. And that's it. It was the job was processed sequentially. It's actually the whole basis of all programming, right? But there are no loops in this language. In the original language of cards, it was always sequential. It's like one line. It's like you had to write it in one line, and that was it. There wasn't such a thing as a loop. That's changed. But the concept of a job control language has not changed, has carried over into HPC systems. That everything you do on an HPC system is oriented towards batch processing, where you write a script like this one. We're going to run a script. In fact, we're going to run this script. We're going to submit it to a queue. And here, I think that's my next slide. The concept, what you do is you compose your job script like the one on the previous page, right? You submit it, and while it's running, you can monitor what's going on, but you can't do anything with it. It is out of your control. The most you can ever do is kill it. If you say, "Oh, I screwed up. This is not going to work. I got to stop this because all I'm doing is consuming resources that are just going to eat up my allocation." It also means that because you can't interact with it, there is no interaction of any kind. Like there's no graphical interfaces, and the output always comes to a file. There are no. Now it used to go to printouts. Now it comes to a file. But in the old days, it just produced a printout, and that was the result of your program. So why this is relevant and why I'm spending time on is I suspect some of you have never experienced this. It's entirely, if you have, I wasted time on this, but I can't know that beforehand. But you also need to understand why it is essential, and that is, it really is essential. This really is an essential model for a really large problem, a large computing job. If you've ever experienced the problem of running a program that runs for days, you totally understand what I'm talking about. You can do that on a desktop, and probably some of you have, but you know how difficult it is to monitor it. And if your system crashes, you're screwed. Whereas an HPC system is made that it doesn't matter if it crashes, you'll get something out, and it won't, you'll not have no idea what happened. Anyway, the point is, it's made for big things that run for a long time that you cannot just monitor all the time. You can't just sit there at your computer terminals 24/7 for a month while this job runs. So, and it's like I say, it's not at all. It means that there is no such thing as a graphical interface. You have to, unless you're doing something weird on the system wasn't really designed for, and people do that. But anyway, I'm getting off on a tangent. So what we have to do, so to run MsPASS on what next question is how MsPASS runs on an HPC system. It is possible to run it, to install it as a Python package. You can find instructions for that in our user manual. I would not recommend it. If you have a local cluster that you want to install MsPASS on, I would not recommend that approach. And the problem you run into is the very reason why we containerized MsPASS. MsPASS runs in a Docker container, or we're going to run a package today called Apptainer, which functionally is similar. The container essentially encapsulates the software environment. So if anybody who's worked with Python for any length of time, it only takes a little while that you suddenly realize I screwed this up. I've got some competing packages that don't play together, and everything's broken. So there are solutions like virtual environments and so on that you can get around that, but it's still a pain in the butt to deal with. And one of the great things about a container is that it gets rid of that. We could release a container. You're using our container now for version 2 of MsPASS. You know that everything in it works together. Whereas if you install a package yourself, good luck. It may or may not work. You'll run into weird problems that you can't know what's going on. It's really can be hard to track. So anyway, it's a really important feature of MsPASS that it's containerized, and it's where you're going to find, as you guys build your career, I suspect almost everything is going to be done that way real soon. But for either of these approaches, it's important to understand on an environment like this, what it means by a service and the service that MsPASS runs. So a service as a newer concept in fairly new computing. It's fairly central to the cloud stuff we're going to talk about on Friday, but there's some words about it, but it basically means that something you can produce as a black box that you interact with it through some API. An example is the way we've been interacting with the database. The database, we talk to it through the PyMongo API, which is find one, and those kinds of things, and or the MsPASS extensions. That's what I mean by an API, that you interact with the service. And as long as you know the rules, you can do what the service get the service to do what you want. So in MsPASS, there are actually we like to think of it as there are 4 distinct services. There's a thing I'll call scheduler, we'll talk about later, and workers, which are the things that actually do the computing. We have a database service and a front end. When you're running on GeoLab, you're running on the front end, which is a Jupyter Lab server, or Jupyter Notebook server, or whatever they call it anyway. Now, whoops, sorry, my bad. This shows the idea I was talking about, that a service can be thought of as a black box. So this is how a wiring diagram of how MsPASS works as the services interact. There's a front end which drives everything. That talks to the scheduler and the database. The scheduler gives work to the workers, and they may or may not communicate with the database service, but the front end does all. So that's the idea I mean by a service model. If you could put it as a black box like this, a box diagram, wiring diagram, you're thinking about services. Now, the weirdness of HPC, or should I say not weirdness, a feature of the way you have to deal with this on HPC, is HPC computers will see when we configure this, you ask for a specific number of nodes. So in this example, I've asked for 3 nodes. If my job asks for 3 nodes, I could configure my virtual cluster from these 3 nodes. And it would use those 3 nodes. What my objective is to make that look like this. And that's essentially what our configuration is going to do, is we're going to take say, if you're going to use 3 nodes, this is how this is how I think of it, but I'm going to use 3 nodes to do it. And I got to tell the launcher, as I would call it, how to do that. Because it doesn't, anyway, we don't have any way to know that automatically. So this is a specific example how you might do that, a layout that you might choose for how you set up those services. It isn't unique, but it's one way to do it, and it's kind of the way we standardly do it, that you put one node, you put the database, front end, and scheduler service in the one node, and you do the other nodes are workers. So all the work that these guys do are tied up, or you keep them busy, running the database, front end, and the scheduler, and you put other work here to the workers. So each of these services, in this case, would be distributed among 5 nodes. But you could move these around. I could put that database there. I could put front end there. It doesn't. The abstraction of the thing as a service means that you don't know the difference. The only thing that changes is the performance. And so there are issues about how you set that up, and we don't have time for that at all. So anyway, what we're going to do today, and about start this, got to get moving on this, is we're going to run this launcher, new recent development in MsPASS. Actually, it's a Python-based launcher. And what it does is run a little Python script that instantiates a class called an HPC cluster launcher, a big, long, verbose name. But when it's created, when it is initialized or constructed, it launches a database server somewhere. It launches these other things as well. It launches a scheduler and a front end, and it launches workers. And the configuration that's driven by a configuration that we're going to set up right next. And it got to tell it how to do that. And we're going to talk about that in just a minute. And then when we run it, we're going to run the job by the run method of the launcher. And what the launcher does, which is a little weird, is it's actually running off by itself. It's essentially does its own submission of this script to the notebook server, and runs a Python interpreter it essentially moves the program to the notebook server and says run it. So that's how it works on an HPC cluster like this. And so that's all done. Actually, let me go back up here. We should look at this configuration. This script, that's what it does. Let's look at that right here before I go on. See, here's creating this launcher. That's exactly right here. Here's the launcher. You create it here, and then you run the script. Or actually a notebook. That's the job we're going to run on Frontera. So let's go there now. Let's see. Let's start here. How are we doing on time? Okay, 11:30. Okay, we're fine. Now, what I recommend you do, I realized something I didn't in here. If you've looked at this, actually the simplest way, to do these you could do them all in GLab. You could launch your own you launch a new terminal, and you could connect to Frontera like that way. That's what I already did right here. So what you want is one session on Frontera, and you want one locally. So I'm going to leave this one here to be my local file. And I'm going to show you what you might also want to do, though, is where did I put it? So I'll show you how. I'll just do an example. SSH, my username, Pavlis at frontera.tac.utexas.edu. So you need the same command, except you change the username to whatever Ian sent you. And it'll come back like this. And then you do your password. And then you have this obnoxious duo authentication thing. I don't know what you guys had set up. I have a thing on so-called Duo app, and it comes in with the number I need to. It's a magic number I have, which is currently is 527878, and I'm in. So, can everybody confirm you're in on Frontera, that you can log in? Work on that. Do I need to leave this up to see what I did? It's pretty strict. If you log, it's just like logging into any computer system. Any problems, questions with that? So, what you're going to want to do over there on once you've, I'm going to go on this one because it's easier for me to show you. So that's my home directory on Frontera. What we want to put all this work, we have quite a fairly large data set we're going to work on here. There's a pre-built location for each user called scratch $scratch. That's me. You need to do the same thing and find out what that is for you. Okay. Everybody with me? I hope. See, that's what I just did. PWD, CD to scratch directory. The reason is we're going to need this. We're going to need this in a few minutes. In fact, like instantaneously. Okay. So go back to the instructions. If you look at the instructions, you see this. Now I'm not going to do this because I already own these files. This would just copy it back to myself. You saw that what you're going to do is copy the files that I own here and make yourself a local copy. We actually could have done this by linking to this shared folder, but it's just easier, I think, if everybody has their own for this exercise. So what you're going to want to do is just copy and paste this, like, whatever your local copy is on your machine, and then paste it in here. I don't want to do it because it'll just it's like overwriting files on themselves. But questions about that? That'll take a couple of minutes to do for each of you, but we can do something else while that's happening. Okay, because there's something else important we got to do. Any issues? Pretty straightforward, I think. But unmute yourself. Okay, all right. So the harder thing we got to do now is go in here. In these TAC files, there's this file called HPC launcher .yaml. We've adopted the use of so-called YAML, pronounced YAML files in MsPASS because it's somewhat simpler than some other formats like XML, which a lot of people use. It stands for yet another markup language, and that's what it is. But if you don't use YAML, it's pretty simple. And the only thing that's important is like another example of key value pairs. Okay, so what you need to do in this, you can edit this right here live, and I'm going to you'll need to change some things here. So this one's left alone. Let me just talk about what these are as we go down them. There's the container is where the MsPASS container is stored on this system on Frontera. Don't change that because that points to a specific file that we will be running. The next one you have to change. And that is after you copy that with this command right here, you're going to produce whatever your directory you're working in, PWD, whatever that resolves to, you need to replace Where am I here? So if that, you might come out to be, it might come out to be something like 62445. I don't know. I just made that number up. Slash Joe. To wherever you wrote those files. That's the working directory. Because that's the configuration we have to tell it. It's like, this is where you're going to run from. Is that reasonably clear on time? So in other words, to really say it again, whatever this resolved to, well, in that case, it's actually this one, where the equivalent thing. But whatever you resolved in this step right here, where you CD your base scratch directory, you did whatever that is, you need to substitute into this line, into these lines. So every time you see scratch all this junk, in fact, if this had a nice editor, we could do that. I don't think it does. Maybe some of you are better at Jupyter Lab than I am. What you could do is a global substitution of scratch 1 04465 / Pavla / ES 2025 to whatever your working directory is. So you have to change all that. The only other one of those you have to correct is down here. So basically, that's the problem. We haven't found a good way to do a nice clean substitution into this configuration file to add this kind of structure thing. We could, but we haven't done it yet. So anyway, that's the main thing you're going to do. So while you're doing that, let me talk about by whatever method you're doing that with. We could transfer it over to Frontera and do this too if you know how to use VI or something like that. But anyway, what we have to define. Let me just talk about what we're building here. We're pointing to a top level directory where everything should be found. It's like the run directory where this job is going to run. Log directory says that's the directory where you should write log files, just like we did in the local copy here. There's a log directory we ran yesterday and earlier. Database directory says, where is the database? When we started a session like this one, we pointed to it the same way. It's the top level directory in GeoLab. This is whoops, I hit the wrong button. This is comparable. It's like, where does the database live? What directory does the database live in on Frontera? By the way, it'll be created with this job. You don't need to create the directories like we did on GeoLab. And this is just a scratch space that the DASC, as we're going to call it, uses. So we just need to define that directory so it doesn't go somewhere else. The next things are not something you will want to change. It's workers per node is set in this case by how many cores there are on this node, each node. We're going to ask for all of them. Although we're actually only going to ask for 40 on the node we're running from, because we're going to do everything on one node. If you had remote node, there are 50 cores per blade or node on Frontera. But we're doing here with this primary node workers is only setting aside 40 of those. We're using 40 of them for this job on the node you're running on. There will not be a remote node. This just sets. You don't need to change this. It needs to know the cluster name. None of these that's just a start. None of these change. Auto, or most of these things are auto. And Slurm is the name of what's called the job scheduler on Frontera. It's just a piece of software that determines your job, where you are in the job queue. We'll use it here in a minute. It's just an application. This is all kind of like things that are in there they're important, but they're really kind of not something you could dig into this later. The point is none of these change. Everything from here down, the only thing, I'll reiterate, the only thing that changes is these directories that are listed here. I'll just tell you what they are. What we're doing is running this container, and it has to be told where where those file systems are. So this is something that's passed to the container when it's launched that says, I want you to mount that directory that you're working in. So this -B with your working directory must point to your working directory because it says that's where I'm going to, that way it'll appear by that same name when you run it. Home is the same way. You wouldn't have to do this, but it avoids problems. You could actually remove this and it would probably run just as fine. But it's easier if you leave it that way because it avoids conflicts that can happen otherwise. But anyway, so what you need to do that, and once you do that, get that editing completed, you'll save that. You're editing it here live. Then you're going to want to use these commands to copy you want to go to that directory at a terminal. So you would do like on this terminal. Let's see, where am I? Terminal here. Is that the one on Frontier? Yeah. So CD MsPASS tutorials. I just could show you again 2005 TAC files. So what you're going to want to do is with this command, SCP is take. I don't want to do that because I'll overwrite my own stuff and I edited it already. But what you're going to do is use this. If you've ever used SSH and SCP, you'll recognize this. Just copy all the contents of the TAC folder, TAC files directory to my scratch directory. Here is this one. So I actually could have put this, but I could have said here, well, actually that wouldn't resolve because I'm on the wrong side of this connection. So whatever you get, whatever this is, again, it's that where I got the wrong buncher. Oh, I see what happened. Somehow I did that. Again, this is the central thing you need to have. So you're copying that in that configuration file, and you got it when you run this. That's where you got to copy them to. So I suggest that I'm going to give you all about 5 or 10 minutes to do that. And I'm going to, let's see, let me stop sharing and we can, if something I needed to help somebody, you could raise your hand or whatever, and I'll see if I can help you. But otherwise,
there's a Q&A question, a TAC question specifically.
Is that here?
Can you see the Q&A?
Okay, you saw me do that too. TAC uses a dual log, dual credentials thing. When you created your account, you had to say how you were going to do that. And I think they give you options like texting to a cell phone or an app on your phone for doing that. I used, the app that I used was this one, if you could see it. I don't know if you'll be able to see it or not. I guess phones don't show up very well, and that's not going to show up at all. That didn't work. It's an odd one that's it's a dual authentication thing called Duo that we use here at Indiana, and they support it Frontier at TAC as well. Maybe who's my if there's any other, I don't know what other options, but anyway, it had to be done when you were configuring your account, and I don't know how to tell you how to fix that if you can't remember what you did.
Howdy.
Yes,
This
yeah,
is
I
Mitchell
saw
from
that.
TAC here. I've jumped in.
Yeah,
In the Slack for day 3, I don't see the Q&A, but on the Slack day 3 MsPASS, I have dropped in the documentation for TAC MFA.
super. Thank you.
Absolutely.
Oh, there you are. Yeah, I didn't know if you were here or not. Okay, good.
Whole time.
Okay, thanks. We see how people are doing. Raise your hand if you've got all that configuration done, and or
Yes, I've been able to do that. Yeah, thank you.
I did a lot real fast there, but like I say, I repeat, to go to the directions. If nothing else, just read the directions we give you there on that. I should maybe show you that back, and I'll leave it up. That's probably the thing to do right now, actually. So just follow the directions are all right here. Maybe it's time to ask to people to raise their hand if you already got the files copied over. Where are we? Is anybody? How many people have gotten the files edited and copied?
I'm done.
Okay.
I'm good as well.
One problem is that I think probably editing problems. It's too bad there isn't a good way to edit these files, because that configuration file editing thing is awkward. I know that's probably a barrier to some of you, and I don't know how many of you've used a lot of Unix commands, stuff like this before either. So I think we're gonna have to blunder on in a few minutes and just, because hopefully you can do this stuff offline with those instructions. See, if you're not real familiar with Unix, all HPC systems, as far as I know today, use some flavor of Unix to drive drive the cluster. Not true on cloud systems, but it is true on HPC systems, as far as I know. And so you're using the Unix shell, and if you're not familiar with that, I can see it's got to be a problem. There's not. There's quite a few instructions there. So, if you have any questions, you need to do. What are your problems? Can you tell me if we're having people aren't finished, obviously, what do we need to do? What are you having problems with? I can't know if you don't tell me. Well, then I'm going to blunder on about what we need to do. So I'm going to go to this terminal over here that I launched on my Mac. Make it a little bigger. See, maybe can you see that? Okay, let me make it a little bigger.
Yes.
So you want to go to this working directory where you copy this stuff. Now I had mine in this. I added the other folder, which you won't have, but you should see there this, which is the WF directory and exports. Now we put the exports in here to avoid the problem of running web services to bring down all this metadata. It's pretty huge for this problem. It takes like an hour so I exported a working database that contains a site, source, and channel collection. In these, these exported as JSON as a format for them. And so the first job we're going to run is, well, that's interesting. Where's my jobs? Did I throw them away? See, interesting. I did save my own stuff. Okay, well, I'll have to go back here because I didn't do it. All right, well, interesting. Forgot that I'd blown those away. So I got to come back here and catch up with you. Let's see. Where am I? Where's my local terminal? I got to get this stuff out of the way. Oh, this is the wrong thing. No wonder. That was a completely different job. Okay. So over here, I got terminal. This is the one locally, right? So I got to fix now that I've messed this up because I edited this configuration file though. Where was that? Didn't I change one of these? Yeah, I did. And I got to save it. Where's the save button there? Okay, how do I save this? File, save YAML file. Okay, now I got to go back here. I need to go back here and copy these files. Oh, what was that scratch one? Oh, I can't remember. This. This is my cut and paste. So where am I now? Let's see. You get real confused here about where you are. I think it's this one, wasn't it? Yeah. All right. So now I should be able to go back here. So you should see something like this, where these are the files you should see. We're gonna now. This is when I talk about batch processing. The Slurm command is the name of the package that's used on Frontera for managing jobs. Okay, and let me just show you what that looks like. Cat db import.job. The way this job file looks is you typically start with this magic incantation, but these are required. These pound at capital S batch. They are things that you need to tell Slurm about your job. The ones that are important here is that this says that I'm only going to use one node, which is what you're doing. This is the account to charge it to, which is MsPASS's account. This says something about, you'll see that where the outputs come are going to come to a name called MsPASS.something. You'll see with a number. You don't really change these, but this one's important, which is the runtime. this says I'm only going to ask for 5 minutes for this job. It'll go in instantly when I do that. Otherwise, you can sit for a while, because if you ask for a lot of time, you have to sit in the queue waiting to be your job to run. And what I'm going to run is this little this stuff right here, which is really the same thing I showed in that PowerPoint. What you're going to do is actually going to run a fairly elaborate Python script called this one. We're not going to take that script apart, but we're going to run it right now, which is, I'm going to say, where was that star.job? It was import. I can't remember what it is again. You're going to say sbatch db import.job. There's nothing magic about job. I just did that way to distinguish that it's a Slurm job script, not a shell script. And when that's running, I always just use my username, but there's other things you can do here. It says that it's waiting. It hasn't run yet. So that job is sitting in the queue and waiting to run. I have to wait for that to finish, or at least start, before I submit the second job, which is process.job. Let's look at that while that one's running. It's very similar if you look at it. Actually, you can look at this on Jupyter if you want. You don't have to do the command line things I was doing here. But see, this stuff is all the same, except now I'm asking for 2 hours. But I'm only asking for one node, and that's the same charge number. The outputs, everything else is the same. And everything, this is all the same pretty much, except I added a timing thing here, how long it runs. But I ran, this is the MsPASS launcher right here. It runs like this. It creates this launcher Python thing, which launches all those services, and then I'm going to run the notebook called RF processing, which you could look at. We'll look at later if we have time. That's going to run all this processing stuff. So let's see if that's done now. Wow, it's still in the queue. I don't know what the status of. You guys may have a better entry, because maybe I can't remember how this was set up. But that's really surprisingly long for a simple 5-minute, asking for only 5 minutes.
You do have someone asking in the Q&A that
Okay.
the job pending with the reason resources while everybody is on priority. So is there anything that can be done or should be done about that?
I do not know the answer to that. Where's my Zoom window? I'm lost in the. Oh, here it is. We may have to just wait, and maybe we could just come back with. Let me start over and show you this again. So I'm a little worried I made a mistake right here. That you may not have this stuff installed. You may need to do this. Underscore this.
I think that command was part of the db import So
Oh, it was, wasn't it? Okay, that's how it worked then. Okay, so that's what I thought. It's like, well, it should work, and so other people tested it. So okay, I think we're still sitting and waiting, maybe, huh? Wow. Oh, you know what? Maybe it's, we might. I want to try something. That's good use way to try this. I'm going to kill that job. So you have to give this magic number 7253943. I've seen small get messed up before. DB import. I'm going to put this on so-called normal queue. I think that's the name for it. Michael, is that the right? Michael, right? Is that right?
Mitchell, but let me double check
Mitchell.
something really quick for you.
Yeah.
You guys should have. Here we go. You need to attach a reservation name.
Oh, okay.
Your reservation name is capital M. In your SBatch script, you're going to have to add SBatch-R.
Capital R or lowercase?
Double checking that right now, actually.
Okay. Well, that explains it because the small q gets a little bogged down sometimes. I was going to go to normal, but we could. The system has multiple so-called queue names for like long-running jobs and normal jobs and small jobs. It's the that's probably why we're all sitting there, because we're all trying to get into the same workspace, and there's just aren't that many nodes in the small queue.
Okay, you can use -- reservation equals.
All right, hang on a second here. Ah,
Let me pop back. You've got your, yeah, that should work.
equal. Then there's
Capital M, little s.
Is that it?
All the rest of this is all caps. PASS.
Yeah, right. So if I don't know what you got, what are other are there other inline command line editors that people might know that they could use on at Frontera? I just always have been an old VI guy, so I don't have any trouble using
We
this.
have Vim, we have Nano, and we have Emacs. Nano is probably the most user-friendly.
Mhm.
It's the most similar to Word or Notepad.
Does everybody see that? I'm gonna try submitting this now and see if it goes right in. It should.
Let's verify. Yeah, let's verify that's the right way to do it.
Ooh, something went wrong.
Rest node configuration is not.
Permission is not available. Maybe it's because I used the wrong. What queue should I have been in?
Let me check which queue you guys' reservation is in. It should be. Oh, that's what's going. Partition small.
Oh, so it would have been right if I hadn't changed it. Okay. Ah, there it went.
And then that reservation should be up and running. Let's run that SQ with your username again.
Oh, I didn't thought I'd killed the other one. Which one's which?
The bottom one is
the new
higher
one, right?
number. Yeah.
I must have made a typo. Why did it not kill? Oh, it's the wrong. It says cancel.
That's right. Yeah. I was wondering. Yeah. Yep.
That's an old. There was a different job. I have old. Okay. Why does it take that? It takes skill, but it doesn't do anything. I ran across this before. It's a different job. I used to use a different one of these. I can't remember what it's PBS or one of those. There's a different job schedulers, and it's kill like that. But anyway, but I'm still sitting. That's bizarre.
Let me see that SQ one more time. There it is.
Oh, there it's running. Okay. So did everybody?
Yeah, that was a little bit of a delay. I'm not sure why.
Yeah.
But anyway, yeah, that reservation, you can either add it to the SBatch line or the SBatch.
Oh, we could have done that, right? I could have done the. Let me just.
SBatch -- reservation. would have worked as well.
So I'll show you that example right now. In other words, I'm going to get ready to, I could say, I'm going to do the other one, which is the processing job. So I can say dash dash, or is it that be before that? I think I have to do it before it, isn't it?
Yes, that's correct. Before dash dash reservation equals capital M. Yep, you got it. You got it, Gary. There it is.
Did everybody see that? Whoops. I don't really want to start that until I'm ready because this other thing has to finish first. The other one may be finished by now. It just finished, yes. So let me show you that what happens as a job finishes, it'll generate this output file. Remember I told you a batch job, that's all you get. And this is what it's going to label it. MsPASS, they get that. It also updated the database. I can't interact with it easily this way. That's another whole story about how to interact with the database interactively on an HPC system. We're not have time for today, but that's what we just did. It ran successfully. Let me look at that more carefully, make sure it did. This is just a bunch of verbose thing when it launches. And it says error code 0, return code 00. That's all good. Doesn't mean it finished correctly, and shows that that's the output of the job, that it showed that it imported all that stuff into MongoDB. So now we are ready to do what I just said was a second ago, which was sbatch dash dash reservation, right? Equals MsPASS processing process data dot job. So it's queued. It might sit there for a while. So I'm going to leave that there for people to kind of work on for a minute. Let's take a 5-minute break. We're going to, well, 6. Let's reconvene at 12:20. You can work on this for a little bit. Try to see if you get your job submitted. And again, like I said, we have the directions are there. Although we're missing this about reservation that we didn't see before. And if we don't get it done today, you could do this offline later on Frontera to see how to play some games with this. It's a big problem. So if you don't even get it to run, that's okay. I just want you to see how this kind of thing goes and what you have to do to make it work. So we're going to reconvene at 12:20. Yeah.
Before we break, can we do that group photo thing?
Oh, yeah. So I'll do a stop share.
Yeah.
All right. Timer went off. Okay. Interesting. Okay. I thought I'd show you quick. Here, let me, I don't know how many people have gotten this anywhere, but my job here has been running. So come on, where are you? Been running 8 minutes now. So this will run for about 45 minutes. I thought what I'd show you next before I go on to the next part is I probably should show you what you're running. Where's that job? There it is. You can peruse this at your leisure, but this is a complete workflow to go from raw mini-C data to a set of receiver function estimates. And you know, I'm not going to dwell on every piece of this, but basically what it does is it starts with the raw mini-C data. It indexes them. It then sets P-wave travel times and windows around the P-wave using these functions. It windows data around these P-wave travel times. it's going to use this construct, which we'll talk about in a minute, for the map operator. And then it goes from the mini-seed data, it does some sort of pre-processing and windowing of the mini-seed data. It saves data in a so-called time series. Then it goes and it's pretty much parallel to what you did in that pre-course workshop. In fact, it's almost identical. There's just very few variations. But what it does differently is at the end, it runs this stuff. This part runs a set of, one's a quality control thing, which actually was run in the pre-processing thing too, to select, get out data has try to remove, not even try to deal with anything that doesn't have a signal. And then it runs this receiver function at the end and produces a bunch of receiver functions for like 100 events. It produces a few thousand of them, or 10,000 or so. I can't remember the number it comes out. Well, it looks like more than that because it says here. So anyway, that's what you're going to run. That's what you're running right now, if you get that far. What we're going to do while that's running, though, is we're going to work on this notebook in a few minutes. But before I get to that, I want to give you a short lecture about some other other elements of parallel computing. So we're going to work on that notebook in a minute, but I want to talk about a few other things here before we go on. We just sort of I just talked about these in generalizations before. And one of these is this idea of what's called a scheduler worker. In my pre-course lecture, I gave you a little bit of material about that, but not a lot. This is part of a generic framework for parallel processing that we use in MsPASS. So we actually could do either one of a package called Dask, and another one Spark, or PySpark is the Python version of Spark. They both do functionally things very different, very the same. I mean, they're kind of like dialects of the same language, but what they do is essentially identical. And we use Dask by default because it's more closer linked to Python. It sort of behaves better in general. Whoops, my bad. So what really is important in them is that they're really a generic mechanism to run jobs parallel. So let's talk about what that means. What does it mean by running something in parallel? If you go, this is now to remind you of something that I had a little thing in that introductory lecture, the pre-course lecture. There's this commonly used thing about baking a cake analogy, that if you had to make 100 cakes, if you did them one at a time, you'd have to do the same thing 100 times. You'd have to, whatever the sequence of events, if you did it serially, you do the steps to bake a cake. So you mix, get all the materials, you mix it up, stir it up, put it in the pan, bake it, pull it out, whatever, and frost it, whatever. A parallel version of that is that if you have 20 people to help you, you say, you take that one, you do this, you give all the stuff, they do all of them do the same tasks in parallel. While at the same time, they just do the same tasks. And when they're done, they put their cakes out on the end of the line. Well, that's essentially what this generic scheduler does. Is it gives the scheduler is like the person, the foreman, was another name for it, gives the tasks to the bakers to do. You take this cake, you take this cake, you take that cake. Do your job, and when you're done, tell me, and I'll give you another one. And that's basically all they do. It's really simple, but the way it's actually done under the hood is this computer science concept called a directed acyclic graph. You don't really need to know what that is, other than I think I'll show you here in a minute, because most of the workflows I've ever seen with MsPASS to do cyclic data processing are real simple. They don't have any complexity. This graph in some ways is kind of in the way, but it's a very generic way to do parallel processing. There's another thing called futures, which is an alternative way to do this than using what we're going to call MapReduce. In some cases, you could do that. I'm not going to, that's a different topic. We've kind of still been playing with it. So mostly what we advise you to do is what's called the map reduce paradigm. Here's a figure pulled off the internet, which is what that means, is an example of a map reduce algorithm is driven by a set of files. So you'd have this example has 3 instances of a map operator that would take the data off a file, do something to it, and produce out 2 different outputs. This one produces this output. The reducer kind of mixes things, or reduce function can mix things from different parts of this stage of the output and put them together. The definitive example of reduce in seismology is stacking. So I think it's probably clearer to look at this specific example from our documentation, which has a little animation that goes with it, which is how a typical sequence might work. And actually it's close to the one you're using, we're running right now. You have a reader that creates an instance of a thing, which I have this tag here, bag RDD, which means it's the best way to think of it is it actually is, in fact, can think of it as a Python, as a list that doesn't fit in memory. So it's like a Python list that doesn't fit in memory. And the process works by pulling data out of the container, this bag or RDD for Spark. You pull out a datum, the data it wants to work on, run it through, this case, a MsPASS function dtrend, which is the same as the OBS5 version, filter the data, passes that on to filter, window to cut it down, arrival SNR just computes the signal noise ratio of a particular, in that window, whatever that's defined, and then save. I just made that up. So, okay. Then it saves data somewhere, which would probably put it into the database or write files. So this just illustrates how that would be parallelized. This animation illustrates how you'd parallelize that with 2 processors. Each of them do the same things, working their way through this container until they're done, and then there's kind of stray stuff at the end that they have to process. It's very straightforward what it has to do, and that's exactly what we're going to see animate in an animation of real data processing on GeoLab shortly. So that's why I say that how that works is going to be clearer when we look at some things in GeoLab in a second. So these are just repeating what I said, I think. Okay. There are some weird restrictions about to work in this paradigm, most of which are not really a very big deal. But for map, most of what we do is map all the algorithms in MsPASS, and if you write your own made up of other functions, you have to write it in terms of a function, meaning it's something that has a data input as arg0. The first thing is the data that it's supposed to process, and a set of arguments that describe how to do this, go into this algorithm, and it must return something. That's the map operator, is done through the function. So the task is defined by the function, and it has an input and an output. So in a way, the algorithms act like Unix filters, but they have but it's Python that's providing the input and the output. So the function return of everything should be the same type, or you're asking for trouble. It doesn't actually have to be, but it causes all kinds of chaos if you don't. But the return definitely could be a different kind. Like, so for example, you could put it in time series, and you could or put in a time series ensemble and come out with a time series if you stacked it, for example. The functions, I talked about that last on Monday, is that one of the issues is that to be working in this framework, they should never throw an exception unless it truly is a fatal problem that you want it to abort. So something like a memory fault is a fatal error. and you have to stop because nothing will work after that. But if it's if it's just a problem with this data set or this data input, it says it'll throw an error and it'll kill it. That's what MsPASS functions do. But if you write your own function, it has to follow that model. Reduce has some other weird properties, and it's one of the reasons why we actually have really not used it very much. Enough. Anyway, you can look at the algorithm section in the user manual, and you'll see all the algorithms that are available and how they work. So now, when you actually do this, it's always a good idea to start by a serial workflow. I don't know how you do it otherwise. So it helps you understand what the algorithm, what the flow is, and it's easy to convert it. This is a couple general pieces of advice here that I'll tell you that right now, one of the first rules about running parallel work is if you don't have to, don't do it. If you can, because it introduces all kinds of additional problems, and you almost have to get it working. And the best advice is you always get to working on a subset of the data in serial first, because then you got all the arguments to all the Python functions, right? Otherwise, you're just asking for trouble if you have to submit batch jobs and look at the output over and over and over again. It'll take forever. So really the right way to do it is prototype things on a desktop with a smaller set of data and then prepare it for a big system like HPC. And that's why this timing data is important, because you need to establish from your serial prototype sort of how long it takes to process a particular chunk of data. And then if you have 100 times that, then you know that if it takes 1 minute to run 10 and you have 1,000 of them, you're gonna have to multiply it by 100. So you're gonna only need a couple minutes, or an hour, whatever. So, and then you have to scale by the number of processors roughly. And we'll get to that more in a minute. So what I wanted to show you is how the programming interface is actually really simple. How do you translate a serial prototype into a parallel version? So this is an example. We'll see loops like this in examples that we had in that what you ran to start before the class even started. So in this case, it's create a cursor and you loop over the cursor. We were showing examples like that. So this is just generic. I'm saying read data, run procedure 1, procedure 2, and save data. The way you parallelize that is, well, this is one way anyway. You still create a cursor, and then one of the ways to do it is you create what's called a data frame, which is we have a function to do that. So you can then, that basically converts reads the whole block of data into a data frame that may not even fit in memory. And then you run this method df2bag in Dask, which converts we do processing for MsPASS in what's called a bag, which is a list that doesn't fit in memory is the best way to think of it. And then the key difference is right here where you have these things that it says, well, I got the name, this is the container, it creates the container in the symbol my bag, and then you run on the bag a map operator running that function. This one has the same pattern. The name of the container, the function, the method name is map, and the argument to it is the first argument to it is the function name. So these go 1 to 1. So if you have a working thing like this, they just go across 1 to 1. Then the only other weird thing is that the way this works is nothing happens until you tell it to go. And the way you do that is you call the method of the bag container called the compute method. that says go. And once you do that, it initiates the calc. Nothing happens actually if you were stepping through this code. Nothing, it just instantaneously comes back until you hit compute. And it'll sit there for however long it takes to do the computation, and then it'll come back and it'll return. This is a similar form for a different thing, which is ensembles. Only it's the same idea that you're driven by a list to convert to query. You could create an ensemble, and then you process it with the same functions. Pretty much all the processing functions we have in MsPASS now support all 4 data types automatically, as if they were. In other words, if you process an ensemble through a routine like dtrend, all it does is it means it'll automatically process everything in the loop and all the members of the ensemble. So a lot of algorithms are better done through using ensembles, and you can just run them through this way. But again, it's the same thing though, that the way you do the conversion is every line that was a function you call, like this one, proc1, is the container's name, symbol, the method is map, and the first argument to the function is the name of the function. There's more to it. We'll look at specific examples in a minute in this notebook. So I'm going to stop there. That's just a detail, I think. So what time are we doing? Ooh, I want to move along here. I am going to largely.
Gary, there's a
Yeah.
question.
Oh yeah, where is it? Raised. Okay, yeah.
Hi, just real quick. I noticed that my processing.job on Frontera was finished really quickly. So I checked the output and it says it couldn't find the .sif file. So I think I missed something at the very beginning.
I can tell you what
That's
that is. That's right here. When you did this YAML file,
Yeah,
did that get altered?
I did, but only the first 2 slashes, the home and the number. I didn't
Oh yeah,
touch the one
you should
behind.
not. You should not have altered this.
Okay.
Sorry, I
Okay,
should have
that
made that clear. This one should have been left. I should have put a comment there that said don't alter this. Yeah, because that's the only location of that container, and it's a shared directory, so you can read it.
Could you
Can you see it?
quickly leave that up so
I
I
will.
can
I
copy
will.
it?
I will.
Thank you.
So what I want to do next, everybody look at the session 2 notebook.
Okay, got it.
You're got
Thanks.
it. Good. Okay. Whoops, wrong button. So you shouldn't need to do this again unless you re-enter it. But if you do, you got to go that process again. I'm going to just kind of go through this and just talk about this quick. These are just initializations. We see a lot of this is standalone. I'm not going to dwell. This is something you should read through, but I want to just show you some things here, which are that what we're going to work on. There's a couple things that what this workflow is doing. I just wanted to show you what they're doing. So here's a 1-3 component seismogram set. This is a big, gigantic earthquake. And this just shows you the waveforms. What this is about is reinforcing some things we talked about on Monday, but shows you that one of the things this workflow has to do is, I talked about the transformation matrix in the object because the data is not in cardinal directions. So this example just shows you why you would do that and what it does. So when we run rotate the standard, it transforms the data to standard coordinates. And then we're going to run a slick thing that Brian Kennett wrote about decades ago now, used in receiver function processing, called a free surface transformation. It's non-orthogonal transformation of the components that makes splits it into the best thing you can do for P, the longitudinal component, the SV and an SH based on the orientate of the expected direction of propagation. So that's what this apply, that runs a function called apply FST. And so what you got is, this is from the bottom up, is this is SH, SV, and this is the P component. So it's just, that's being run in this workflow. The other one that's in here that's described is one of the things you got to do with a large group of data like this is about 80% or more of it, 90% of it is nothing there. We had a fairly low magnitude threshold for where we pulled this data set in. It isn't true with what's on GeoLab here, but so what you want to do is look at signal noise ratio and say, is there anything there at all? And MsPASS has a fairly sophisticated version of that in this thing with this headlessly verbose name called broadband SNR QC. But what it writes is all this stuff. It has all these different metrics that it computes for what the signal noise ratio for that particular window of data is. So it requires, on a thing like this, it has to look at the spectrum of the pre-event noise, and it looks at the spectrum of what you call your signal window, and it gives you a signal noise ratio based on that actual measurement of the spectrum of the noise, pre-event noise, and the signal amplitudes. And it's a really useful way to get rid of all the garbage, because otherwise you have, it's like, I think we used a magnitude cutoff of like 4.7 or something like this when we assembled this data. So 90% of that stuff is just junk in the workflow you're running on Frontera. But anyway, that's what this is running. What I want to mostly focus on, I'm not going to run this here because it'll block on this, and I don't want to do that right now. But this will run a serial job on only 100, the first 100 seismograms that are in the data, and you'll get some timing data on it. It takes like a minute. I could do it, I guess. Maybe I'll do it. What the heck? So, because it illustrates what I just talked about. So it runs exactly the functions we just looked at: rotate to standard, apply FST, to free surface transformation, and this function called broadband SNR QC. And it doesn't save anything in this case. Oh, it went faster than I thought it did. So it took 17 seconds to run 100 seismograms. So there's about 20,000 or like 10, I don't remember what the number was in this data set, but that's the serial time. We're going to run it in parallel, and one of the things you could play with in this, and I don't think I already asked you any questions of this, is how well it scales. The number of processors is I think it's 40 or 50 we allocated, or no, I'm sorry, here on GeoLab we only have 4. You got 4 CPUs you're going to get, so you're going to have 4 workers running when you run the parallel version of this. So if it was perfect scaling, you divide by 4 what you'd estimate. So if we take, say, 10,000 of these, there'd be 100 times more, and we would divide by 4. That would be 25, and so we'd get like 25 times 17, whatever that is, something like somewhere around 500. If it was 100 times that, it would be 1,700 seconds, which is half an hour. So anyway, that's the idea. Now, what I want to show you, the thing I mostly wanted to do in this exercise that's really helpful is a feature of Dask, which is really slick, which is when you get to this line, and it'll produce this output. And what I want to do is when you get there, launch this, and it should create a new window like this one, which is called their Dask diagnostic, or it's a new tab. It should create in the same notebook with you. So nothing's happening right now because we're not running anything, but we're going to, in a minute, right now, this talks a little bit about what's there, these figures that are there. and we're not going to, you could scale if you had if you were on a cloud system like Jupiter, like a GeoLab, I mean, and were willing to pay for 50 processors, you could upscale it to that at this stage. If you're allowed, you can't go beyond 4. So it does nothing. You could run this, but it won't really do anything. Let's run it though, just because it should allow it. It didn't really change anything because we were already set up for 4 workers. So we run this. This is just creating, this running. Okay. So let's go over here while that launches, and I'll talk about what it does. Where am I? Something's covering me up here. Oh, where's my tab? There it is. See, now it's running. This is a real-time display of what's going on when this job runs. Right now, it's just kind of getting its act together. There's several tabs here that are useful. Now it's actually doing real processing. So this is sort of the tasks as they're being done. This is useful to look at, I think, which is status. And it talks about this. I talked about this DAG or directed X. In this case, it's a bunch of lines, just like my animation was. And it shows you that this shows you the list of how many things are in this bag. That's technically something called a partition. You can see it working its way through it. So the blue ones are done. The red ones are in process, are sort of loaded, but not doing anything. The green ones are what are running. So you can see the things light up as it goes along. So it's actually working its way through this data. 4 processors running simultaneously. You can see them sort of, it isn't continue, which one finishes, some will finish faster than others. And so this status panel here is showing you in real time all that's going on. It tells you how many are done. Shows you how much data is being used. You got to watch this thing sometimes, because sometimes a lot of workflows will generate a lot, use a lot of memory. This one's fine. This shows you how it's worth useful to look at the worker tab, and it shows that it's doing pretty well. It's using about 80% of all the workers' CPU time. So it's running pretty close to top flat out on the 4 workers. It's using close to 100% CPU. I can't remember what this one shows. This is just the same thing the other one shows. But this is kind of the main one you use if you want to just watch what it's doing. This is the green thing is just telling you the status of it. I know the other one is profile. Telling you is really useful for, actually, maybe that won't come up. Actually, it won't come up until it's done, I don't think. Let's go back to this notebook to talk. You can watch that thing go, what this profiler can show you. These are words that talk about what you're seeing there. Same thing we just looked at. The profiling tab, it's kind of a weird display, but it's really a good way to find out where a workflow is spending its time. You can look at the explanation here, but it basically says that each of these things, as you mouse over them, will tell you how much time it was spent on that particular task. Like read data, it says spent 2% of the time there. Average time was, or its total time, I can't remember which it is. So it must be average time that it spent was 640 milliseconds. So what you could do with this is it's basically like a call stack, and you could use the information there without going into the details. If you want to really tune a parallel workflow, lots of times you could go through this thing and figure out, oh, I'm spending 99% of my time waiting for something, IO on something, for example. I need to rethink about how I'm doing this. That's what it's for, like any profiler. you can read, like I say, there's some nice words in this notebook. You can read about it at your lake. You saw this display as it was running in real time. And this is groups. Is it done yet? Maybe it's done. We can look at that one in real time here. It might be done. No, it's still going. The groups thing tells you something about more. It's another kind of a profiling thing. So like this is like how many processing time, percentage of the time, and how much completed it is right now. So it's like, so this is basically the reader or the initiator from sequence. This is the sequence of processing tasks, and this is the writer in this workflow. So where are we? Let's look at the graph. Oh, it's almost done. So I did that really quick because our people did you find the real-time graph display? Any problems people are having with this? I was kind of blazing through that because I know we're kind of running short on time here. But that was just a quick demo anyway. So it's like, say, this thing is meant to be self. The rest of this is about some variants that you can read about, other ways you could do some of this stuff. They actually are essentially equivalent ways to do the same workflow. And I talk a little bit here about things you could do to tune your workflow in a parallel system, but that's about the best we can demonstrate for now in the time we have available. So is it finished yet? Probably is getting close. It's done. Profile show now? No, it still won't show. There's something wrong with that. I don't know why that's happening here. Maybe there's something about GeoLab wouldn't let the profiler work. I don't know. But usually that graph, that thing is live. So let's go back here and see what it did. It should get some timing data when we ran it. That took 350 seconds to do 5,270. And here's the point about scaling. Up here, it took, that's why I decided to run it, took 17 seconds serially to do 100. So it's about 50 times that, 5,000 something. So about 50 times 100, that's going to be about 1,000 seconds. It actually took, what did we say, 400 seconds? 400 seconds, 350. So if it was about 1,000 and we were perfect scaling, we could divide that 1,000 by 4, which would be about 250. So we didn't quite get that, but 349 is pretty good, and it's pretty consistent with what we saw as the CPU meter. It was showing about 80-90%. So it was usually those problems were the reason it doesn't parallelize perfectly is because it's IO time. It has to do wait on IO, and that will slow it down. So there are weights in there that determine so that you don't keep the workers 100% busy. But anyway, so that's about that. Let me go back to Frontera here. See where my job ever finish? Oh, still running. It's got to be almost finished. Output file was already there, but it's not going to be complete. So let's chat for a minute. We got a few minutes. We started a little late, so we can maybe wait for this. I think it takes about 45 minutes, so this should finish real soon. Within the next couple of minutes, if it doesn't really matter. What we do is we can look at the output. But
just finished, actually, Gary.
Oh, did okay.
Yeah, it's
Oh, yeah, it says CG. Yeah, it says CG. this line, so it went from R to CG means completed doing something. I can't remember what it stands for. So now we can look at the output. Two, 3, 5, 3, 9, 9, 0. So if we were to run that notebook, these are what would come out of the output lines of the notebook. So there's a bunch of stuff it echoes at the beginning that it says this when the launcher was running, just telling you what it did. They're debugging if something goes wrong. But it says I launched 40 workers. So we were running this job on this thing with 40 workers. And there's a run line that goes. So what this is showing, everything was echoing some data as it went along. These are things that would have appeared in the Jupyter notebook output boxes if you run it under the notebook. But now they get thrown out to standard output instead of being thrown on the. So it's kind of ugly, but at least it shows you that it worked. Okay, so it actually went and finished. And I don't know why it has these. We see this a lot. I don't know this thing about sending large graph of such and such a size. It doesn't like that, but it's a common warning we get with large seismic job processing. So it took like it says that it took 2,600 seconds, which is about 45 minutes. So this processed, I'm trying to remember the number. I think it was 100. You could add, does tell you something, does it tell you how many of these? It doesn't add them up. But my recollection is it's about 100,000. Yeah, we did about that in 45 minutes. It did about 100,000 seismogram input BC files from beginning to end to produce a set of receiver functions. And I'll show you what it produced. I forgot to say that. The files are here. I can't show you the database very easily without some more work. It produced the outputs of the receiver functions are these cryptic names that are just meaningless because all the information is in the metadata. I just didn't give them fancy names. But the their intermediate stuff is it produced the seismogram and time series versions of the data. A little detail, I got to stop here in a minute, but one of the details, if you look at that notebook that we ran, has a capability that you can restart the job in the middle. That's one of the reasons why I think it's a good idea to always, if you're processing through a sequence like this, where you produce, so we did some time series processing, and then we did some seismogram processing before we did a receiver. Those are like 3 phases of this algorithm. So we first produced time series, then we produced seismograms, and then we produced receiver function estimates. And they all, we saved them in 3. I just did it. I keep them in 3 folders. That helps to keep some organization. But the other thing it does is if the workflow gets interrupted, if you estimated the timing wrong, which happens all the time, and it took longer than you thought it was going to, the workflow could be made that from the database, you could look at what's done and then restart where you left off. It's one of the really useful features of driving the system by a database, which would be almost impossible to do. It would be much harder to do with files. Yeah. Raised hand. Go ahead. Yeah.
So the time that we put into the batch job has to be quite accurate, actually, what we expect the system to give us in terms of computation time.
Yeah.
This is what we expect.
Yes,
if it's shorter than what it
you know,
needs, it will break.
Exactly. That's a really good point of that on a batch system. You got to tell it how much time you think it's going to be. And that's another reason for serial prototyping or then doing a smaller workflow or get an idea what it is. But what you have to do is if you're doing something new, I gave 2 hours and I knew it was going to be 45 minutes. but I left it 2 hours. And that's kind of a typical rule of thumb, maybe factor 2 or 3 to be above what you think it'll be. What happens on an HP system is that there's kind of a gaming the thing you trade off about how much you ask for, how much time you ask for, and how long you wait. So you could just ask for a lot of time, but you're going to wait a long time. So, you know, I could have asked for 24 hours, but I probably would have waited for 24 hours. So what you want to do is, that's why you want to know the estimate kind of about, but you got to be generous about what you actually ask for to make sure that you'll finish. Because data processing is never quite as reliable as you start running a bunch of simulations on a HPC system, and kind of you run a benchmark and you go, oh, this is going to take about an hour per run. And so you run with 10 nodes or whatever. Say, I'll just always ask for like hour 20. If you have really, it's always the same calculation. But data processing could be a little flaky because unless you know that in this case, it's like you do, you know, it's like you don't know how many, every event may have a different number of survivors to work through the thing. And they have different numbers of good data that survive different stages of the processing. So it's kind of not unpredictable, but it's irregular. What it'll be is how long it'll take. So you have to give a long answer, but you give it a generous thing, but not ridiculously long. That was a good question.
So the longer the time, usually the lower the priority in the queue as well. Like, and the higher the time. If you give it 24 hours, it will wait a long time until it is
Ian knows this better than me, but it's kind of, that's been my experience, is like it's almost like how longer you ask for, the longer you wait. Usually the systems have ways to bypass that. You know, it's like sometimes some systems have where you can even buy nodes. Some universities have places where you can, you know, have your own custom nodes, and if you submit to that queue, it's always empty. You always trump anybody else who comes in. But there are different ways that's what the job scheduler has to do, is decide how it goes. And there are tools to look how busy it is too. And that's what happened to us, right? When we started out, we couldn't get in because the queue is really busy. And until we gave this I think it was busy because we had a reservation for it. So until we put reservation, we weren't getting in. You have any comments, Ian? You're still there?
Yes, I'm here. Well, but I think you pretty much covered everything could have mentioned. So
yeah, I was gonna jump in and say the same thing. You pretty much got it down. The only thing is like Slurm does backfill. So if there's jobs that are shorter that it can fill in while it's waiting for new jobs to start, it'll adding time is always better for your Slurm S batch script.
Could you actually add time when it's running? You mean, is that what you're saying?
No, I'm sorry. Adding the time variable is what I meant.
Variable. Yes. Okay. Yes.
How long you think the job's going to run?
Right.
Yeah. So, you know, it's always interesting, right? And I think there are a few papers on this topic where people actually inspect the current state of the queue and try to figure out whether there are like empty spots that you can fit your job in with the backfill. You know, one of my previous colleagues at Tech actually even wrote a paper on doing that with the AI model, which is actually quite interesting too. So, you know, there are various ways that you can kind of maximize your usage and, you know, with the lowest amount of wait time. But then, you know, as a normal user, you probably don't really need to go for that extreme. Just a mere job is, you know, most of the time it works fine.
Yeah, I did use, Ian has a great graphic of this analogy, and we've used in other versions of this class of it, of Tetris. The job scheduler's job is just like Tetris. You've got a slot of how many nodes fit, how many nodes you want to do over a certain time. So the time axis is how tall the Tetris is, and how many wide it is how many nodes you want to run. It's got to fit in the slot. If it doesn't have a slot to fit it in, it won't insert it into what it does when it tries to optimize where it inserts those slots. So It's an interesting computer science problem about that scheduler. I'm sure there's many probably $1 million things that I invested in that software for all I know. But anyway,
But couldn't you give it some margin? Say I want to use ideally n nodes, but then like if you only have like minus plus 5, you can like adopt that.
well, you have to, yeah, well, yeah, that's more like what we're going to see. I think what you're describing is more like what we're going to see on Friday when a cloud does it automatically adjusts like that. Ian says that refers to HPC systems as bare metal because they don't have their scheduling is really kind of fixed to this batch processing mode. So what you start with is what you get for the whole time you have it. That's a good thing, and it's really well tuned for simulation because then you gotta have it, right? But for data processing, it's actually not ideal because your needs will change in a workflow, and these are typical examples actually. That if you had automatic scaling, which you do in the cloud, you might only need a couple CPUs to start the work. You like that, it most efficiently run that way. But when you start really doing heavy computing, you need, I said, give me as many as I could take, I'm willing to pay for. But it doesn't work that way in HPC, and that's a really important point about HPC. And it's like I say, it's going to be a contrast on Friday when we talk about cloud systems. That there's a different way to do the scheduling that's dynamic. That as the need grows, in fact, that happens to you, has happened continuously while we've been running on GeoLab here, is that maybe, I don't know if Sarah's been monitoring this or not. They have a little tool that tells you how many nodes are being used and how many CPUs are being used by this group. And it'll wax and wane with time. And it's it's really a much more efficient way to use the thing in data processing like this than an HPC system is for that reason. Because if the job's very, I'm dwelling on what's our next topic, but that's Friday's topic, really a big topic. Good question. Well, we're already way over. Anybody have any more burning questions? Don't feel free to, we've had very little activity on our office hours. Please come. Just chat. Nothing else. We'll talk about how to do certain things. So, okay. Otherwise, I think we're well over time. We should probably let people go. Sorry, I went through a few things kind of whirlwind, but again, I reiterate, I tried to make all these exercises self-contained. You should be able to read them, and they actually should just work. And hopefully you'll get the lesson. And the quizzes will reinforce what you learn by reading through that notebook. But listen, that's okay. Okay. All right. Well, I guess that'll be it then. Toodaloos.